Section 1.4, we're going to talk about types of functions. So, functions are used to describe or model real-life situations. New functions are created every day. Functions such as the relationship between memory required for an iPod versus an iPad. Apple didn't come up with just this breakthrough technology. Okay, all these formulas and functions and models that came with it mathematically changed the way we look at things as well. There are three types of functions: constant, linear, and nonlinear. So we're going to talk about all three in section 1.4. So let's talk about the constant function. So the constant function, every x has the same y value. It is a horizontal line, and it's represented as y equals some number. So we have an xy plane, and we can draw a horizontal line where this right here is the y-intercept, okay, and it's a horizontal. The domain for every constant function is all reals. The range is whatever that y value is equal to. Okay. So we could say that this line is y equals 2, so the range for this example would be y equals 2. Okay. If we drew a line down here, y equals -2, domain would still be all reals, but the range for that would be -2. Constant function. Then we're going to talk about linear functions. Linear function we know as y equals mx plus b, remembering that m is our slope and b is our y-intercept, so the point 0, b. The domain for linear functions, all reals. The range for linear functions, all reals. For word problems, it's important to recognize that slope can also be called rate of change. rate of change. So that's going to be something per, keyword per something. Okay. Each different units, but the keyword per, PER, that represents slope. Let's look at some word problems. So the first one here, we have wages earned by an individual working X hours at $6.25 per hour. So, example 1. Okay. So we're talking about working X hours, and the rate is $6.25 per hour. So you want to think to yourself, okay, well, if I'm working for 5 hours, okay, I'm going to be making $6.25 times the 5 hours. If I'm working 11 hours and I want to find how much I'm making, $6.25 times the 11 hours. If we want to do it for a general equation, okay, we take the 625 and we're multiplying it by whatever our hours are. Okay, general form, X hours. We know that Y equals mx plus b. Okay, m is the slope. So in this case, our slope is 625. Another key phrase, okay, is that it actually said in the problem $625 per hour. So we have some units per another unit. And that right there also tells us that slope is 625. If we look at this example right here, it says the amount of tuition and fees due for X credits if each credit costs $75 and a fixed fee of $56. So again, the amount of tuition and fees due for X credits if each credit costs $75. So example 2, we have X credits, and then each credit is $75, and we have a fixed fee of $56. So this fixed fee means that I'm going to be paying $56 no matter what. So let's say I'm taking 6 credits, and I wanted to find out how much my tuition is going to cost. It's $75 times the number of credits plus that $56 that I have to pay. If I'm taking 4 credits, I would take the $75, I would multiply it by 4, and then I would add the $56. So if I want to change this to a general equation, I took $75, times it by the number of credits, and I added the $56. mx plus b tells us then that our slope is 75. Okay. So in this example, it didn't actually say per, but if we wanted to write that out, okay, let's say, okay, let's say they wanted you to interpret the slope. Okay, we would write this as dollars per credit. Okay. So here they didn't give us that word, but we can make it so that it is using dollars per credit. So that's determining slope from word problems. Let's just say I give you points. So slope, we talked about, is represented by m of 2 points, x1, y1, and x2, y2. Our equation is change in y over change in x, which you know as rise over run, or y2 minus y1 over x2 minus x1, or y1 minus y2 over x1 minus x2. As long as you're consistent, you can do it in either order. Positive slope looks like this graphically. We're increasing from left to right. Negative slope is decreasing from left to right. Zero slope means that we have a horizontal line. Okay, you can think about it if you're skiing, okay, and you're skiing on a slope that has no slope, you're not going anywhere, you're just on flat land. And then undefined slope is a vertical line. So if you're skiing off a cliff, you're not skiing, you're just falling straight down. So undefined. So let's find slope. First one, -1, 2, 3, -4. So we're going to label each point. We're going to label this x1, y1, x2, y2, and then we just plug it in the slope formula. So -4 minus 2 over 3 minus a -1 is going to equal -6 over 4. And we're going to simplify that to -3 over 2. Always simplify the fraction. The only time it's acceptable to use a decimal for slope is in word problems. Otherwise, leave it as a reduced or simplified fraction. Let's say I give you -2, 3, and 1, 3. Label this x1, y1, x2, y2. So it's going to be 3 minus 3 over 1 minus a -2. 0 over 3. When 0 is in your numerator, we simplify that to 0. So 0 slope. So this right here is a horizontal line. Versus if I give you these 2 points, 4, 1, 2, x1, y1, x2, y2, 2 minus 4 over 1 minus 1 gives us -2 over 0. We already discussed that you can't divide by 0, so this becomes undefined. And it's really important to write it as undefined. Don't leave it as -2 over 0, because I need to know that you know the difference between 0 in the numerator, 0 in the denominator. Okay, and this would be a vertical line. then you can also find slope looking at a graph. So let's say we have this graph here, 0, 5,000, 10,000, 15,000, 20,000. And this represents number of songs. And then we have 20, 40, 60, 80, representing gigabytes. And then we have this graph. So the first thing we want to talk about, okay, is y is 0, 0 an accurate point. Okay. Or in other words, why can 0, 0 exist in this word problem? Okay. So gigabytes, sorry, this should be iPod memory. That would be useful. Okay. So why is 0, 0 an accurate point? Okay. We can say 0, 0 is an accurate point because 0 songs means no or 0 memory is used. Okay. So 0, 0 does exist in this type of problem. If we have 0 songs on our iPod, it wouldn't be taking up any gigabytes. Okay. As we add songs, then it takes up gigabytes. So that is why we're increasing. Okay. Then if I ask you to find the slope, okay. The easiest way, I always do it to be consistent, especially when we get to nonlinear, always pick the endpoints. Always pick the endpoints. So our one endpoint was 0, 0, and then this point is clearly defined as 80, 20,000. So we're going to plug this into the slope formula. x1, y1, x2, y2. So when we plug this in to the slope formula, I'm running out of room, so I'm going to have to erase this. Okay. But we denoted y2 to be 20,000 minus 0 over 80 minus 0, and that comes out to be 250. So that's our slope. Then another possible question that I could ask you once we find the slope to be 250, if they say interpret the slope, they just want you to tell us what it means in words. So what does this 250 mean? This means that we get 250 songs per, there's that keyword, gigabyte. Okay. So 250 songs per gigabyte. When figuring out the units for rate of change, it's always going to be your vertical units. So in that last example, it was songs per, and then your horizontal units. So that's why we said songs per gigabyte. Gigabyte were our units for the x-axis, songs were for the vertical axis. Okay. And that should make sense because, like we talked about, slope is change in y over change in x. So it would be these units per x units. So whenever you're asked to interpret the slope, that's what you would use. So for example, if we look at this word problem right here, it says in 1985, 95 billion was spent on advertising in the US. In 2005, $270 billion was spent. Find and interpret the slope. So we can write down 1985 was 95 billion. In 2005, 270 billion. Just a little note, for all applications, time is always your x-axis. Okay. Time is always an x-axis. So this would be my x1, this would be my x2, which would make this my y1 and this my y2. Plug it into the slope formula. 270 minus 95 divided by 2005 minus 1985. So we figure that out, 270 minus 95. Divide that by 2005 minus 1985. And we get 8.75. Now, careful, 8.75 is not my final answer. These numbers were in billions. I dropped the billions to find slope, but I need to put it back on at the end. So our slope is 8.75 billion. And then it wants us to interpret it. So we would say our dollars was our vertical unit, 8.75 billion per year. Okay. So our vertical units, money spent, per horizontal units, in this case, years. Okay. So slope, an important concept for linear functions. We're going to be talking about linear functions in chapter 2 as well, so this is just an introduction, but really important to understand the concept of slope. Why is slope such an important concept in this particular section? Because now we're going to talk about the third type of function, which is nonlinear functions. And slope plays a big part in determining the difference between linear and nonlinear. Okay. So a nonlinear function, okay, is when the slope isn't constant. So in other words, the slope changes between different points. It's not the same. Okay. Another way to figure out if it's a nonlinear, okay, the graph is not a straight line. And another way, okay, x is raised to a power that is not 1. So nonlinear functions. Some graphs of nonlinear functions. Okay. We have the famous y equals x squared. We have y equals the square root of x. Y equals x cubed. Or we can even have things like y equals absolute value of x. Okay. Even though the power is 1, okay, for x, the absolute value, okay, changes the graph compared to y equals mx plus b. You can also tell whether or not something is linear or nonlinear by looking at the points and comparing slope. So for example, if I have points 1, 3, 5, 9, corresponding y values 5, -1, -7, -19. Okay. We want to look at the slope for each of these. So the difference from 1 to 3, 2. From 3 to 5, 2. From 5 to 9, 2. 5 to -1 is -6. -1 to -7, -6. Oops, that would be 4. And -7 to -19 would be -12. So the slope here, -6 over 2. Slope for the second part, -6 over 2. Slope for the second one, -12 over 4. All of these reduce to -3. So this would be linear because each slope is identical. It's constant. So again, I just took the difference between each one and then I put slope is change in y, which was -6, over change in x, which was 2. If I give you these values, 1, 2, 4, 7, -2, 0, 2, 4. Change from 1 to 2 is 1. From 2 to 4, 2. 4 to 7, 3. This would be 2, 2, 2. We compare the slope. First one is 2 over 1. Second one is 2 over 2. These are not equal. Okay, we can even look at the next one, which is 2 over 3, not equal. As soon as you have two slopes that aren't equal, nonlinear. So comparing comparing the slope between the values. Real world examples, let's say we have a 100-gallon tank. Two scenarios. The one is being emptied by a pump at 5 gallons per minute. Versus we have another 100-gallon tank. A hole is drilled in the bottom and it empties in 10 minutes. We want to know which is linear, which is non-linear. So again, the difference between the two is a constant slope or a constant rate of change. So we look at this first one. Keyword right there, per. This pump is consistently emptying this tank at 5 gallons per minute. So we know that every minute 5 gallons is being emptied by a machine. It's constant, it's consistent. So this would be linear. Versus a hole is drilled in the bottom. We know that if we have this 100-gallon tank, okay, and we drill a hole, the water is going to rush out at first and it's going to empty really fast. But then what happens when you have just a little bit of water left? Okay, it's going to drain a lot slower. So because the water is emptying really fast and then at the end it slows down, our slope is not consistent. So this example right here would be non-linear. Okay. So constant rate of change. Is it there or not? And that is it for section 1.4. All right, section 1.5, still talking about functions. Like I said, functions are important in every aspect of life. Okay, so first we're going to talk about increasing and decreasing functions. If you want the actual mathematical formal definition, you can read it in your textbook. Okay. But I'm not going to make a concept more difficult than it needs to be. Okay, so basically we are increasing if the graph is going up from left to right. We always read left to right. So when you're reading a graph from left to right, if it's going up, it's increasing. Decreasing, the graph is going down from left to right. So we're reading from left to right, and if the graph is going downward, we know that it's decreasing. Increasing and decreasing. For linear functions, if the linear function has a positive slope, then it is strictly increasing. Any linear function with a positive slope is always increasing. Strictly just means always increasing. If a linear function has a negative slope, reading from left to right, strictly decreasing. So a linear function is either always increasing or always decreasing, and you determine that by slope. Constant functions. Okay. They are neither increasing nor decreasing. Okay. Remember, constant function is just a horizontal line. You're not going up or down, you're staying the same. So constant functions, neither increasing nor decreasing. Nonlinear, okay. It differs for each equation. So you take one, each nonlinear function as it is. When discussing intervals of increasing and decreasing, you always use the domain. So you use the x values, use the domain to describe. So for example, if we look at the y equals x squared, okay, we're going to start reading from left to right. So from left to right, we are moving downward. So from here to here, we're moving downward, so we are decreasing. Okay. But we have to discuss it in terms of x values. So from where to where on our x-axis are we decreasing? Well, my smallest value, since I'm going to continue going out this way, negative infinity to x equals 0. And then from here to here, our graph is now going upward. So we are increasing from 0 to positive infinity. So you notice, especially with the decreasing, it's negative infinity. It has nothing to do with the y values when you're describing it, okay? The only thing we care about the y values is if they're getting bigger or smaller. Well, here, because it's decreasing, the y values are getting smaller, okay? But that's all we care about. Our x values is how we're going to describe it. So we're talking about these intervals. I want to talk about interval notation before we do a couple more examples. So interval notation. From now on, we're going to use this for domain, for range, increasing, decreasing, and the list will go on as we go throughout the semester. But so far, domain, range, increasing, and decreasing, I want you to use this notation. Okay. So we had set notation, which was dealing with inequalities. So -2 less than or equal to x less than 1, or x is greater than 3, and so on and so forth. Interval notation uses brackets. Okay. And this means that our value of x is between a and b. So b is our highest value, a is our lowest value. And brackets means that we include a and b. But we also use parentheses. This means that x is between a and b. But now if you look, we're not including a and b. You can mix them up. You can have parentheses a comma b bracket, okay? Or you can have bracket a, b parentheses. And then just make a note that negative infinity and positive infinity always use parentheses. Brackets means that it could be that value. It could be a, it could be b. But we can never actually be negative infinity, infinity, because those aren't numbers that we can actually grasp. Infinity represents a number that just keeps getting larger and larger and larger, but you can never reach infinity. It just keeps going and going. So that's why positive and negative infinity get parentheses. Another symbol, the U, okay, this means or. Mathematicians, okay, we don't like words, we like math. So if we can get rid of words even as tiny as or, okay, we will. So from now on, U equals or. It's called a union. So let's practice with some examples of writing interval notation. So if I give you x is greater than or equal to 1. X is greater than or equal to 1, you want to first think about, okay, what's my smallest value if x is greater than or equal to 1? Well, this means we're starting at 1 and we're going bigger. So 1 is my smallest. And I'm just getting bigger and bigger and bigger, so I'm going to positive infinity. This always gets a parentheses. It's greater than or equal to, so that gets a bracket. X is greater than -2. Think about the smallest. I'm starting at -2 and I'm getting bigger. So -2, and if I keep getting bigger, positive infinity. That gets parentheses. -2, it's not greater than or equal to, so it's parentheses. Let's say I have -3 less than x less than or equal to 4. So x is between -3 and 4. It's not equal to, so parentheses, but it is equal to over here, so it's bracket. Let's say x is less than 3 or x is greater than or equal to 6. Okay. So start with the first one. X is less than 3, so 3 or smaller. So my smallest values are going to be -infinity. My largest value is 3 because we want to be 3 or less. -infinity always gets parentheses. This is not an equal to, so that is parentheses. Or means union. And then x is greater than or equal to 6. So we're going to be 6 or bigger, always parentheses. It's an equal to, so bracket. So this right here, this whole thing is your answer. Oops. X is less than 2. So 2 or smaller means smaller. 2 is our highest. Always parentheses. Not an equal to, so parentheses. And then if I say -infinity is less than x less than infinity, you have 2 ways to write this. Parentheses, -infinity to infinity parentheses, or this also is all reals. So either notation works for me. Interval notation, extremely important. This is all I use, so it's really important to understand how to use it and what it means. Okay. So let's go back to increasing and decreasing. If I have this function, we'll do f of x equals 1 minus x squared. So 1, 2, 3. So we're at 0, 1, 1, 0, 1. So it looks like this. And I want to know where are we increasing and decreasing. So again, remember increasing, we're reading from left to right. So from left to right, I'm increasing, 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 increasing. So I stop here. So I'm increasing from, and now we got to look at our x values. Well, even though this is going down, okay, it's always extending. So our x values are going to -infinity. And then we stop when x equals 0. And then from here down, we are decreasing. So we're starting at x equals 0, and we're going to positive infinity. Remember, we're always talking about the domain. So the domain for this side is to positive infinity. Let's look at one more. I don't have an actual graph, but I'll just plot points. 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We'll put a point at 0, 0. And we'll put a point at 2, 6. And we'll put a point at 4, 0. 1, 2, 3, 4. We'll put one at -2, -6. And -4, 0. 1, 2, 3, 4. So it'll look like this. Oh, beautiful. Okay. Okay. Same question, increasing. Where is it decreasing? Okay. So we start from left to right. So from here, we're going down, so we are decreasing. We're still decreasing till right here. So I'm going to be decreasing from, looking at my x values, my domain from here to here, negative infinity to -2. Then I'm going to start at -2. We're going up, 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 still going up, still going up. So we're increasing from here to here. Well, my domain for that section, -2 to +2. But we're not done yet. Now we have to go this length. So from here, we're going down. So we're decreasing. We already have one, so we're going to put a U. And then our domain for this section, we started at 2. And we're going to, our x values are going to positive infinity. So increasing and decreasing, always describing the domain for each. Okay. And then one last concept, I want to talk about average rate of change. So rate of change should sound familiar, okay? Remember when we just said rate of change, that was the slope of a linear line. Okay. Average rate of change describes the slope of a nonlinear. So even though for nonlinear functions, the slopes are constantly changing, we would call an average rate of change the slope of two particular points that we want to talk about. The formula for this rate of change is f of x2 minus f of x1 over x2 minus x1. Hopefully this formula looks very similar to something we've already worked with. It is the same formula as slope. Okay. The only difference is for a nonlinear, we're calling it an average rate of change. We're just saying for those particular points, this is the average slope, because the slope of nonlinear functions will be similar, just not the same. So example, if f of x equals x squared plus 1, find average rate of change for x1 equaling 1 and x2 equaling 4. So here it already tells you what x1 equals and what x2 equals. So now we just have to find what y1 and y2 equals. Well, if x equals 1, f of 1 is going to equal 1 squared plus 1, which is 2. That's going to represent our y2. If x2 equals 4, then f of 4 is going to be 4 squared plus 1, which is 17. That'll be our y. Oh, excuse me. I'm sorry. This should be y1. This should be y2. If this is x1, this would be y1. x2, y2. Once we find x1, y1, and x2, y2, plug it into the slope formula. 17 minus 2 over 4 minus 1, 15 over 3. So our average rate of change is 5. So again, you're plugging in the x values to find the corresponding y values, and then plugging it into your slope formula. And then word problems. Okay. We have this word problem right here. It says, on dry level pavement, the stopping distance for a car traveling at x miles per hour is f of x equals 1 over 11 x squared. Find the average rate of change from 11 to 22 miles per hour. So writing down the important information, x is miles per hour, f of x is 1 over 11 times x squared, notice nonlinear, and they want the average rate of change from 11 miles per hour to 22 miles per hour. X equals miles per hour, so we can say that this is x1 and this is x2. Which means then we can plug these in to the equation to find y1 and y2. I'm going to erase this real quick because I need more room. So I'll write it up here. X equals miles per hour. F of x equals 1 over 11x squared. So x1 we said would be the 11. We plug that into the equation. We get 1 over 11 times 11 squared equals 11. x2 we said was 22 miles per hour. We plug in 22. We get 1 over 11 times 22 squared, which is 44. If this was x1, this is y1, x2, y2, and then just plug it into the slope formula. 44 minus 11 over 22 minus 11 equals 33 over 11, which equals 3, and our units miles per hour. Average rate of change. Same formula as slope, slightly different meaning. Okay. And that is it for section 1.5.